Now let us solve this problem. Find the differential equation of all planes which are constant distance from the origin. To solve this, we'll take the equation of plane in normal form, which is Lx plus My plus n is equal to A, where L, M, N are arbitrary constants which are direction cosines of unit vector parallel to normal plane. Also, we know that L square plus M square plus N square equal to 1. Okay, we take these two equations to make or eliminate the arbitrary constants L, M, N to form a partial differential equation. Now let us start solving this. So we differentiate equation number 1 partially with respect to x. So differentiate equation number 1 partially with respect to x. We get L plus, so we are differentiating partially with respect to x. We get L plus 0 plus n into dou z by dou x is equal to 0. That means L plus np equal to 0, which implies L equal to minus np. We can keep this as equation number 3. Now we differentiate again equation number 1 partially with respect to y. Okay, differentiate equation number 1 partially with respect to y. So we get 0 plus m plus n into dou z by dou y is equal to 0, which implies m equal to minus nq. Since we know that dou z by dou y equal to q, so we keep this as equation number 4. Okay. Okay. Also, we have the equation L square plus M square plus N square equal to 1. We have this equation L square plus M square plus N square equal to 1. So we substitute equation number 3 and 4 in this. We get, instead of L square we can use minus NP. Okay, so minus, instead of L square we can use minus NP square, plus instead of M minus NQ square plus n square equal to 1. We can keep n square outside, so n square into p square plus q square plus 1 equal to 1. Okay. Okay, now we can keep n square one side and we can move other side. So n square is equal to 1 by p square plus q square plus 1, or even we can say this implies n equal to 1 by square root of p square plus q square plus 1. Okay, so we get instead of m we get minus nq, instead of L we get minus np, and instead of n we get in terms of p square plus q square plus 1. So we get all arbitrary constants in terms of partial derivative. That is, we get L equal to minus np and m equal to minus nq and n equal to 1 by square root of p square plus q square plus 1. Now we substitute all this in equation number 1, which is Lx plus My plus n is equal to A. We'll do in this in two steps. One is, we'll first of all substitute L and M values and convert the equation all together in form of n. Okay, so we substitute, instead of L we can substitute minus npx plus minus nqy plus nz equal to A. but we have n is equal to 1 by square root of p square plus q square plus 1. We substitute that also, minus px divided by square root of p square plus q square plus 1, p square plus q square plus 1 minus n y, sorry, n instead of n we substitute uh, 1 by square root of p square plus q square plus 1. So minus qy divided by square root of p square plus q square plus 1 plus z divided by square root of p square plus q square plus 1 equal to a. Okay. Now we transfer p square plus q square plus 1 in other side. Okay. So we get is minus px minus qy plus z equal to a into square root of p square plus q square plus 1, or even we can say z minus px minus qy equal to a into square root of p square plus q square plus 1. So this is the partial differential equation, and which does not contain any arbitrary constant, but it contains only fixed constant a. So we can also rearrange this into some more simple form. Now again we can transfer, we can keep set one side and keep other thing other side. So we get z equal to px plus qy plus a into square root of p square plus q square plus 1. So this is the required partial differential equation. This does not contain any arbitrary constant. Keep in mind that a is a fixed constant, and that is not a arbitrary constant. So we now got a partial differential equation eliminating arbitrary constants.